When we are considering a solid material instead of something like a spring, we consider the stress and strain of that material. We're not just looking at the force acting on the object, but rather we're looking at the stress, which is the force per unit area, the force acting on the surface of the object per area of that surface. Furthermore, the stress looks at the orientation of that force. If that force is perpendicular to the surface, if it is across the surface, and a stress, a force per unit area, is a pressure. It has units of pascals in SI. That is newtons per meter squared is 1 pascal. Or it can also be given in pounds per square inch in the imperial system. 1 psi is about 6,900 pascals. You can convert newtons to pounds and meters squared to inches squared and get that conversion factor. When you apply a stress to a material, when you apply this pressure, it results in a strain. A strain is a deformation of the material in response to the applied pressure. Strain in particular is a fractional deformation of the object. It's how much deformation you have per unit size. So that could be a change in length per original length or a change in volume per original volume. And a fractional value is always a unitless quantity because you're looking at the change in the value divided by the original value. How much the material deforms, how much strain it has in response to that pressure, that stress, is related to the elastic modulus of the material. That is an inherent quantity to the material. We're going to assume that it is a uniform material that has just a single type of molecular structure without having the complication of different compound materials. As long as the deformations are fairly small, the stress and strain are linearly related, and the elastic modulus is the constant of proportionality between these two. You will use tabulated values to find the elastic modulus, or you will calculate it based on stress and strain. These aren't things that you'll have to memorize. But the elastic modulus is the ratio of how much stress is applied to how much strain, how much deformation results from that. So it's a measure of the strength of the material and its ability to withstand that pressure. This behavior is similar to Hooke's law. Recall that Hooke's law said that a force is equal to a spring constant times a elongation. And in fact here, our stress is related to the force. The elastic modulus is the strength of the material that's related to the spring constant, and the strain is related to how much strain we have as a result. We can explore stress and strain using a stress-strain diagram. What we do is we apply a stress, apply a force over the surface of the object, and we measure the strain as a result. We have reversible deformations that are linearly proportional to the stress in what's called the elastic region. The elastic region here has a linear relationship between the stress and the strain, and the slope is the elastic modulus. So this is how you would measure the elastic modulus in the lab, would be to apply a force, calculate the stress resulting from that force, and measure the resulting strain. And for very small strains, that would be effectively a straight line. Your elastic limit is the maximum reversible deformation. When we talk about elasticity, we're talking about reversible deformations. Once you apply too much stress and the material stretches or deforms too much, it moves past the elastic limit and it moves into the plastic region. In a plastic region, you have irreversible deformation and you have irregular resistance at that point. You have some places where you have hardening as the material starts to come apart a little bit. Sometimes you have weakening where individual parts of the greater object start to have localized failures and then eventually you get to the fracture point where you've strained the object so much, you've stretched it so much that it just breaks and comes apart.